Hello students, welcome to this lecture. In the last lecture, we discussed about the time dependent Schrodinger equation and time dependent perturbation theory. We learned how to deal with the time dependence of a quantum mechanical system when its Hamiltonian is independent of time. In that context, we defined what are stationary states, what are non-stationary states, and then we looked at those cases where the Hamiltonian has explicit dependence of time. In particular, we were looking at a two-state system, and we are considering the time dependence part of the Hamiltonian as a perturbation to the time independent part of the Hamiltonian. We started with this premise that the total Hamiltonian, Hamiltonian of the total system, be divided into two parts, one the unperturbed part of the Hamiltonian H0 and the perturbation term. All the time dependence part of the Hamiltonian would appear in the perturbation, and those terms which have explicit dependence on exclusive and explicit dependence on the spatial part, they would be considered in the time independent unperturbed Hamiltonian. Now, corresponding to this unperturbed Hamiltonian, we have the corresponding wave functions, because we know how we can solve this time independent part of the Hamiltonian. Psi n0 and E n0 are the corresponding eigenfunction and eigenvalues. Now, since I n are eigenfunctions with precise and definite value E n0, so therefore they are called as stationary states. Now, these stationary states can be written down in their full temporal and spatial form as by taking the spatial part of the wave function and multiplying them with the time factor. This is what we learned from the previous lecture. Now, we have to we will learn what we get by a time dependent perturbation, but we will do that for a two-state system. When we say two-state system, that means we have two time independent states called stationary states, psi 10 and psi 20, and the total system, that is the total wave function, as a response to the time dependent part of the Hamiltonian, we are considering a complete final state psi as a linear combination of these two stationary states, where the coefficients C1 and C2 are now going to have explicit time dependence, because the perturbation Hamiltonian itself is time dependent. So, now since we have constructed this total wave function, its time evolution can be monitored by using time dependent Schrodinger equation. So, in the last class we took this Hamiltonian form as H0 plus H prime, and then we took this wave function as this linear combination, and then we did some algebra, and we obtained that some value, two sets of equations that are shown here. Now, the first equation, like we will just go through the terms once more. C1 is the coefficient corresponding to the stationary state psi 1. C1 has explicit time dependence. H prime 1 1 is the matrix element of the perturbed Hamiltonian when the states defined are psi 1 and psi 1. So, it is essentially expectation value of H prime, the perturbation Hamiltonian, when the state is defined by psi 1 or the first stationary state. E to the power minus I omega 1 t is the time factor corresponding to psi 1 state, which has energy h bar omega 1. Similarly, we have C2, H prime 1 2 is the matrix element of the perturbation Hamiltonian between stationary state 1 and stationary state 2. And in the right hand side, we have got this C1 dot, which is the time derivative of the coefficient C1, and a similar equation for where the right hand side has C2 dot and the corresponding terms are in the left hand side. So, what we see here is that of course, we do not know what are these coefficients C1, C2, and they also have now C1 first time derivative of C1 and C2 as well in these terms. But the other thing that we need to discuss about is this matrix element of the perturbation part of the Hamiltonian. So, since we have got a two state problem, so therefore the perturbation Hamiltonian can be written down in this format 2 by 2 matrix. So where I have H prime 1 1, H prime 2 2 in the diagonal, and H prime 1 2 and H prime 2 1 in the off diagonal term. So this simply tells how the state 2 couples with itself when the operator is the perturbation term, which has time dependent terms. It is normally the case the diagonal element of this perturbation Hamiltonian is going to be 0. So therefore we are only going to consider this off diagonal terms. So when I am saying the diagonal elements are 0, that means H prime 1 1 here in this case becomes 0, and similarly H prime 2 2 in the second equation becomes 0. So the first term in both the equations becomes 0, and we still have this H prime 1 2 H prime 2 1 that would continue to appear in our equation. When I do this and I simply rearrange, because I have got in the right hand side C1 time derivative of C1 multiplied by IH bar e to the power minus I omega 1. So I take all other terms to the left hand side and write down C1 dot, and I see it. So this IH has gone right hand side 1 over IH. I have C2 here, H prime 1 2 and e to the power minus I omega 2 1 t. Look here, I have got a term e to the power minus I omega 2 minus I omega 2 t in the left hand side, and I had e to the power minus I omega 1 t in the right hand side. When I bring this right hand side term to the left hand side, I would have minus I omega 2 minus omega 1 t, and that omega 2 minus omega 1, that is the difference in the energy between state 2 and state 1. I am calling that omega 2 1, that is the energy difference between the two stationary states, psi 1 and psi 2. So this term appears. Similarly, we would have another term in terms of C2 time derivative. Now, what are these C1 dot and C2 dot? They tell me that how, as time evolves, how the coefficients of psi 1 and psi 2 change in the overall wave function psi. Remember, the overall wave function is being expressed as a linear combination of these two stationary states, and the coefficients are C1 and C2. In those cases where the Hamiltonian did not have explicit time dependence, the coefficient C1 and C2 wouldn't have any time dependence. So therefore, we can just take this coefficient at the beginning of the experiment at t equals 0 and continue to use the same coefficient, because the Hamiltonian doesn't have explicit time dependence. But when the Hamiltonian has explicit time dependence, the coefficients are also going to change. So this tells the time derivative of C1, how C1 will evolve with time. Now you would see that C1 dependence that depends on C2, and similarly the second equation tells me how C2, or the contribution of the second state, will evolve with time, and that also depends on C1 apart from other terms. So one important thing is that the quantity of our interest would be actually this absolute square of C1 t and C2 t. So they simply represent P1 t and P2 t, which are nothing but the probability of finding the system at that particular state. So you see, we have got two states system, and our perturbation is time dependent. So the two states are interacting. So at different time, I am going to have different probability of landing in state 1 or in state 2. So that probability is being given by C1 t square or C2 t mod square, and that probability also, these coefficients also help me in writing down the wave function at that particular instant of time. So therefore, these two quantities are going to be very important for us. All right. Now we would look at these two equations and then try to use them for some special cases. The first case is that let us consider, so these are the two sets of equations that we have. Let us first consider the situation where there is no perturbation, so that the limiting case is resolved. So we have, that means we are considering H prime is 0. Now what does that mean? H prime is the only term in my Hamiltonian that had time dependence. When this H prime becomes 0, that means my system becomes time independent. The Hamiltonian becomes entirely time independent. So anyway, so this will keep in mind, and let's see what maths is giving us. So since H prime is 0, so all the elements H prime 1 2, H prime 2 1 are going to be 0. So, that is why C1 dot and C2 dot are 0. So, this is the result when there is no perturbation. What does this mean? That time derivative of C1 and time derivative of C2 are going to be 0. That means C1 and C2 aren't going to change with time. Whatever value they had at t equals 0, that value will persist. So, this falls in picture because we have already seen in those cases where the Hamiltonian does not have explicit time dependence. This is exactly what we had obtained, that the coefficients would be time independent. The moment you start your experiment, whatever composition the state is, that particular composition is retained during the perturbation when the Hamiltonian does not have explicit time dependence. Now, we can, since we already know that C1 dot and C2 dot is 0, so we can find out the value of C1 and C2 at time t equals 0. So, once we have this C1 0 and C2 0, we can construct this wave function, and the total wave function is now linear combination of these two terms. But one thing that you notice is that the C1 0 and C2 0, they have fixed value. So, they do not change with time. So, here the wave function is evolving with time, but the coefficients do not change. So, of course, we know that this is an example of a non-stationary state, because the wave function or the probability density would keep oscillating, would keep changing, but what would not change is the C1 and C2, or therefore, in other words, the composition of the state would not change. So, in other words, we can say that while the wave function oscillates with time, the state of the system is frozen. Where is it frozen? It is frozen at its initial composition. Whatever composition we started with, it remains so. This is, of course, the limiting case when H prime is 0. Now, let us consider another simple case where the perturbation, the H prime, is of course time dependent, but it is a constant perturbation. So, I am taking this constant perturbation as H prime V. So, all along the perturbation, suppose I consider that I am subjecting my system to a perturbation, the value of the perturbation will remain same, but I am going to put it, let us say, for certain time t or certain time t1 or t2, depending on what I want to achieve. I will keep that for that long this perturbation, but during that perturbation, the value or the magnitude of this perturbation is going to be constant. So, when this is the form of the Hamiltonian, so these are the working equations that we have, the time evolution of C1, time evolution of C2. Since the perturbation is a constant, I have kept it as H prime V. So, I would put this H prime 1 2 and H prime 2 1, they are also going to be simply H prime V, because they are constant during this perturbation experiment. When I plug H prime V here, H prime V here, I would get these two equations. The left hand side is the time derivative of C1, right hand side is that I have 1 over I becomes minus I multiplied by C2, and here I have got H prime 1 2 being replaced by V multiplied by e to the power minus I omega t 1, and similarly I have got another term over here. Now, I need to solve these two equations. When you try to do that, you will see that let us look at the first equation. The first equation, time derivative of C1, and in the right hand side it depends on C2. But the second equation tells me the time derivative of C2 and the right hand side depends on C1. So, these two equations are coupled. So, I can actually do substitution of one variable from deriving from one equation in the other equation. Suppose in this case I write C2 as the terms going to the other side, and then I take time derivative of that expression as d by dt C2 and then make that term as equal to this. Then I would end up with a second order differential equation where C2 double prime is simply second derivative of C2 with respect to time, and then I have got a term with first derivative of time, first derivative of C2 with respect to time, and then the C2, the coefficient. The other quantities that appear here are omega 21. What is omega 21? The difference in the energy between the two stationary states that I am considering, and V is the magnitude of the perturbation that I am considering. So, these are the two quantities on which appear in this differential equation. Now, we can solve this differential equation. In fact, the general solution of this differential equation is over here, given over here. So, C2 as a function of time. So, these are time derivatives over here. So, therefore, the value of C2 is a function of time. A is given by this term, where I have A and B, two unknown constants, e to the power I omega t, e to the power minus I omega t, where this capital omega is now described in terms of the two parameters of my problem. One is the energy difference of the two states, another is the strength of the perturbation. So, since I know these two quantities, so therefore, this capital omega is a constant or is known to me, and then multiply that with a time factor over here. What is not known are this A and B. How would I get this A and B? Of course, so you see, since this is C2 of t, so this is a classical initial value problem. So, we can obtain the value of A and B by defining our initial condition and thereby progressing. So, let us do one thing. So, this is what we have obtained. This is for constant perturbation. This is the relation for C2t that we obtained in the previous slide, and these are the two working equations. In fact, we are going to have a term similar to like this for C1 as well. Now, let us set up our initial condition. What would be our initial condition? Suppose we consider this situation that C1 0, that means time t equals 0, the coefficient for C1 is 1 and the coefficient of C2 is 0 at time t equals 0. What does that mean? That means at the beginning of the experiment, I know that my system exists in psi 1 stationary state. Therefore, the probability of finding that system at psi 1 is 1 and the probability of finding the system at psi 2 is 0. So, that is given by C2 0 as 0, C1 0 as 1, that at time t equals 0, C1 is 1. So, this is my initial condition. Now, when I plug this value in C2 at t equals 0 in this equation, I would be able to solve this problem, and this is what I am going to get. Forgive me because I am not showing this exact derivation, but they are rather straightforward. In case you have any difficulty in deriving this equation by yourself, we can always provide you with the detailed procedure to reach to this solution. But in any case, let us look at what we have got. So, we have got this C1t, all the terms that we see, we already know this capital omega or omega 2 1, there are some cosine terms, sine terms, then multiplied by e to the power minus of I omega 2 1. And similarly, for C2 term, it depends on the strength of the perturbation, the capital omega and this time factor. So, these two quantities what I am getting by imposing this initial condition, that my initial state, initially the system was in state 1, all right. Now, so one thing that you would notice is that both C1 and C2 will have a real part and an imaginary part, but that should not bother us, because what we would be more interested in is this probability P2t, which we obtained, for example, by taking the mod square of C2t. Now, when you do that, you would actually get v square divided by omega square sine square omega t, and when you replace this omega square form, omega is given over here. So, when you replace this, you are going to get this kind of term. Now, P2t is simply telling that what is the probability of finding the system at state 2 at time t. Now, I do not have to derive a similar expression P1t. That is because P1t is simply 1 minus P2t, because overall the system, the state is going to either be at state 1 or in state 2. So, if I know what is the probability of finding it at state 2, I already know what is the probability of finding it at state 1. So, therefore, this quantity is going to be the quantity of our interest. In fact, this formula that we see over here is known as the well known, very popular Rabi's formula. And this formula is going to be the central part of our discussion from now on. Alright. Now, let us consider a special case and look at this, because so far what we have done is kind of exact. So, now let us consider this special case where we consider that omega 2 1, that is the energy difference between the two states, is 0. That means the two states are degenerate, they have exactly same energy. The two stationary states that we are considering are degenerate state. Now, when put omega 2 1 as 0, you would immediately see that the prefactor that you see over here would become 1 multiplied by this sine square term, and this will get simplified, omega is 0. So, therefore, you have got sine square Vt. So, the probability of finding the system at state 2 at any time t is simply just a sine square function. Now, if we plot this for is a particular value of v that you would take, if you plot this, this is what it appears, because this is a typical sine square function. Of course, at time t equals 0, p2t was 0, because initially the state was in state, the system was in state 1. So, therefore, the probability of state 2 was 0, but we see since this is a sine square function, this is going to oscillate. Now, this is going to oscillate no matter what is the value of v. Even if v is small, then also it would keep on oscillating between 0 and 1. So, one thing that you notice that if we wait long enough, or if we wait, we will always find a situation where the probability of finding the system is 1, probability of finding the system in state 2 is 1. That means the system has completely moved from state 1 to state 2. Now, just before that, we see, since we are seeing how P2 evolves, so similarly we can see the value of P1, the probability of finding the system in state 1, because this is simply obtained by subtracting P2 from 1. So, the orange line is for P1t, the blue line is for P2. Now, if what you will see here, at any instant of time, you can actually find out what is the composition of the mixture. If you consider this here, this point here, this shows both the states are equally likely. So, 50% probability for each case. In this case, this is exclusively state 2, and this time it is exclusively at state 1. So, the system oscillates between state 1 and state 2. So, this variation of the coefficient is happening because our perturbation is having time dependence. Now, if we look at this equation, we can see we can in fact find out the value of t, the time at which the probability of P2t will become 1. This function will become 1 when Vt will become pi by 2. So, that from that equation you can find out t has to become pi by 2v. So, if you wait and stop, because you are putting a constant perturbation, right. If you wait and you stop your perturbation, switch off your perturbation at exactly at this time t equals pi by 2v, then you can prepare your system exclusively in state 2. Although initially they were both degenerate, now you started with state 1, but now if you switch off your perturbation at exactly at this time, you are going to prepare the system exclusively in state 2. And if you choose any other time, you get different composition. In fact, if you know what composition you want to have, you can choose a time accordingly. One thing that you notice is that for the system to arrive completely at state 2, if the perturbation is weak, it would take longer. If the perturbation is strong, it would be faster, but if you wait long enough, you would eventually be there. So, this is the case when I have omega 2 1 is 0, that means the states are degenerate. Now, let us look at the other extreme, that the energy difference between these two states are very large, much larger compared to the strength of the perturbation. So, because these are the two parameters that I have in this equation. Now, I am telling that two states are far away from each other, much greater than the strength of the perturbation. In that case, the P2, so since omega 2 1 is much greater, so this term becomes 4v square divided by 4v square, 4v square divided by omega 2 1 square. So, this quantity, and since this omega is much greater than 4v square, so I am having sine square omega 2 1 divided by 2t. So, this is the expression that I am getting when I am considering this limiting condition, where the energy difference between the two states is much greater. Now, when I look at this term over here, I see again, just like the previous case, I also have here a sine square function, which is going to oscillate between 0 and 1. Of course, it depends on what is the value of omega 2 1, but then it is, if I wait long enough, it would always go from sine square would go from 0 to 1. Now, but this term is getting multiplied by this factor. What is this factor? This factor is v square divided by omega to 1 square, but now we know this factor is very small. So, therefore, the overall probability for the system to be found in state 2 is never going to be greater than this value, because this can maximum be 1. So, therefore, this becomes the limiting value for the system to be found in state 2. Now, when we plot the probability P2t and P1t, this is how we get. Since the states are far away from each other, you see that both the coefficients are oscillating, but P2t is always restricted by this value. You are never going to find the situation when the state has completely moved from system has completely moved from state 1 to state 2, because now the two states are far away from each other. Alright. So, this is again the other extreme we discussed. Now, what we do is that we have come to a situation where we can generalize now to the multi-state system. So far, we have restricted our discussion to two-state problems. Now, for a multi-state problem, again this idea is same. We have the total Hamiltonian unperturbed part, which is the time independent. The perturbation will be time dependent part. Now, the unperturbed system, how should I construct that? Of course, the unperturbed part will be the solution of the time independent Hamiltonian. So, the psi n zeros are the stationary states corresponding to E n 0 energy. So, I am also going to write them as h bar omega n, because I am mostly using omega n to represent the energies in this equation. So, this is the time independent solution. Since these are stationary states, their full spatial and time dependence representation can be obtained by multiplying this time factor with this psi n zeros, and these states, these unperturbed states, are going to follow this time dependent Schrodinger equation, where this Hamiltonian is S0, the unperturbed Hamiltonian, psi n 0 are the unperturbed eigenfunction, and the right hand side you have from the time dependent Schrodinger equation. So, this equation is our for the unperturbed part of the system. Now, since we are introducing a time dependent Hamiltonian, the final state that we are going to propose is going to be a linear combination of all these stationary states. So, the final state we are representing as a linear combination of all these stationary states psi n zeros, but now the linear combination coefficient C and T, we have already seen and learned from the two-state system that they are going to be time dependent. So, then we have this C and T is the coefficient for psi n state, which will also have time dependence. So, instead of writing the full only the psi n, I am writing that in terms of the spatial part, the temporal part, and the coefficient. And this wave function psi is going to follow the time dependent Schrodinger equation of this form. Here the Hamiltonian is the total Hamiltonian, unlike this term over here where the Hamiltonian was only the time independent part of the Hamiltonian. If you recall the similar discussion in the time independent perturbation theory, you would see that we are writing down in those cases the time independent Schrodinger equation H psi equals E psi. Here the governing equation is our time dependent Schrodinger equation. Please note the difference. So, here the total Hamiltonian, total wave function, and all. So, just like we did for the two-state problem, we are defining the Hamiltonian, the wave function as a linear combination of several stationary states with the coefficients which are time dependent now, and the right hand side is IH bar the time derivative of this wave function. Now, the way we did for the two states problem, that we multiplied psi 1 0 or psi 2 0 from the left hand side and did the integration to obtain the matrix element of the perturbation Hamiltonian. We are exactly going to do the same. We are not writing that down, but once we do that part, we will end up with this, where the time evolution of the states is the Ck, the time evolution of this coefficient Ck would appear like this. Let us first realize the terms, and the derivation is straightforward or very similar to what we did in the two-state problem. Here we have 1 over IH bar. I have here a summation of sum over all n states, because now like two-state problem I have now n number of states, and I have here C and T, the coefficient of the nth state, and here H prime Kn, which is the matrix element of K state and N state with respect to the perturbation part of the Hamiltonian, the perturbation Hamiltonian. And I have this energy term e to the power I omega Kn t. If you recall the related expression for the two-state system, there we had C2 dot t as a function of C1 t H prime 1 2 e to the power I omega 1 2. So, in that case only we had two terms, but here we have got n terms. So, therefore, the time evolution of the coefficient of one particular state is going to depend on all other states. Similarly, we can write down the equation, related equation for all other states, but this is where we are going to stop in today's lecture. We will continue from this point in our next lecture and see how we can learn about the time evolution of systems where there are multiple states present. That would be the topic of our discussion in our next class. Thank you for your attention.